Yeah, so I will present the PSF imagejet photometric extraction package. It will be a little bit of a repetition from last science team meeting, introducing, for those who don't know, what it is used for, why it's useful sometimes, when it's useful. But also we will have a hand-on demonstration where we will show you how you can install pipe and also run it. And I will run it on my MacBook Air. So yeah, it takes a few minutes. So we'll see how we'll deal with that. So what is pipe? As most of you know, this is the format that we get CHEOPS data in. Subarrays that are co-added to 30 seconds cadence. And these are like subarrays of the full CHEOPS detector that they're like circular, and they have a diameter of 200 pixels. And this is useful because if you have a big diameter, you can estimate the background, which is important, accurately. While you also have these shorter cadence imagets that have a diameter of only 60 pixels, but they are co-added to 1 second cadence. It means that they are much more rapidly read out. The problem with imagets, or the difficulty if you want to do photometry with the imagets, is that they have very little room for estimating the background. So that is the main idea behind pipe originally, was to do PSF photometry rather than having aperture photometry, to fit the PSF to the imagets, because in that way you could also estimate the background simultaneously. So that was the original idea. That's why it's called pipe. Now, PSF photometry is a little bit different from aperture photometry, in that aperture photometry, you just sum up all the flux that is within a certain aperture, while with PSF photometry, you actually try to fit a PSF. And that means that the different pixels, let's see here, are weighted differently. So the high flux pixels are giving higher weights than the lower in the wings. This has some implications. Unfortunately, so what you need for PSF photometry is, of course, a PSF. And unfortunately, the PSF is not perfectly stable. It's very stable, but it's not perfectly stable. And there's a dependence in particular on location on the detector. So if you have if you switch location, you also switch the shape of the PSF. It also has a dependence on the spectral type of the star because of refraction. You have different, Gianpaolo can switch off your microphone. Thank you. If you have different spectral types, you have different colors. That means that you get different PSFs. That change is much smaller than the change you get from switching location. And in addition, we have a dependence on the tube temperature of the telescope. The therm front 2 sensor measures, is a good proxy for that. It changes the PSF slightly and is also responsible for the normal ramp, as we call it. Now, because this change of PSF, we have developed a way to deal with this by using principal component analysis. And this is useful in various ways. So what we have is we have a library of point spread functions that we are using to fit the observed PSF, the observed for the target. And in order to produce a good PSF that is applicable to that specific target, we use this principal components analysis of the library, where we divide it up into principal components, and then we fit them to the target. And this produces sort of coefficients that are also recorded in the data products. So here you see an example of a target that has been fit by these principal components. And you see there's in particular one component that seems to be changing with time, and this is due to a ramp in this case. So you can use these principal components to detrend your data. And then, so when is pipe useful then, is a fair question. So first of all, if you have imagets, it can be useful if you want to to derive photometry from a more shorter cadence. Like for instance, if you have activity, if you have a flare, like in this case, YZ SETI, a very nice flare, because you have much shorter cadence, you can resolve the flare much better. So here in red, the red points are subarray photometry, and the blue points are the imagejet photometry. So this is a useful tool in that sense. For AMIC, you have a lot of activity. So for time resolving rapid events, it's useful. Another useful thing is that if you have, well, as is well known, here you have an example. If you have, in particular, the faint targets, you typically have a very busy background often, and that can lead to very strong roll modulation. And a way to deal with this is to use the trending with the roll angle. But that is only effective if you have a fairly long visit. If you have a very short visit, you can introduce spurious correlations. So in that case, it can be beneficial to use PSF photometry, because PSF photometry is less sensitive to the background, because you're fitting the PSF here, and the background only contributes in the wings, so they are down weighted a bit. So this is actually the example we will do a hands-on experiment later on, or experiment where we will actually derive the photometry for this specific target. This is from Pierre's paper. When you have a contaminant star, which is also a similar reason, so sort of, and that star is variable, then that variability can affect your photometry. And here you have to the right, you have a curve that shows the sensitivity to this background contaminant for aperture photometry and for PSF photometry. And it is different. It is lower, but it's also different. So if you want to verify whether or not a variation is due to a contaminant, you can do photometry with both methods and see if there is a difference. So here to the left, I show you the photometry that is extracted from a background star, which you can do because PIPE also fits optionally background stars. Here you can see a very strong variable star. Okay, and then finally, which will be increasingly important as the detector ages, as Andrew alluded to, these hot and telegraphic pixels, it's pretty easy to mask them from your fit. You don't need to include them when you fit the PSF. It will introduce a little bit more noise because you lose the signal of the bad pixel, but on the other hand, it was bad to begin with, so actually you gain. And here you see an example of a telegraphic pixel that can lead to this jumps in the light curve. And it's probably also the case for this BD star that we looked at recently that showed a ramp in the beginning. My guess is that it was a telegraphic pixel that just wasn't included in the PSF fit. That's why we didn't see it in the PIPE photometry, while we did see it in the aperture photometry. Okay. So this enables us to use more to do better photometry on particular fade stars. So it's actually not only useful for imagejets, that's the point. It's also useful for subarrays, for fainter stars if you have such. So typically, if you have something that is fainter than 11th magnitude, it can make sense to use PIPE. But if you have something that is, say, between 8th and 11th magnitude, and there's nothing complicated in the background or so, you do just as well with the aperture photometry. So there's no point in using PSF photometry then. Something new since last time is that we now have a pretty comprehensive manual of PIPE that you can look at, and it describes how to install PIPE and how to use PIPE. It doesn't describe exactly all the details of what is happening inside PIPE. For that, we are preparing a paper that will describe this in more detail. So, okay, so I think that at this point, I will stop this share and I will share my full screen. And we'll go back to the live demo, because because it might take it some time. I don't know. So let's see. All right. So how do you install pipe? Well, you do it like I do it now. You type pipe, pip, install, and let's see if this works. CHEOPS, pip, CHEOPS. I mean, pipe is a bit too general name. There are many different other, I mean, there are other packages called pipe. So pipe CHEOPS is what it's called. So let's see if the connection works. How do I do that? Comma, sorry, comma plus? Command plus. Okay. Okay, it installed. I think, let's see. So let's start Python, import pipe. There's a very good connection here, by the way, this Edgerome. I checked it and it was like 300 megabit per second. Yeah, so the first time you run pipe, it asks you to provide the path files, the paths to where you have the data files. So my directories are CHEOPS data. That's what I call it. That's for the data files. That's where you put all your data. And then you also have to have a reference directory with the reference files. We'll come back to what those are. I'll just define them here. Oops. Yeah, okay, so that's it. Now we have installed pipe and we have defined the entries, but we don't yet have calibration files, so or data. So how do you get the data? Well, you get them from the archive or from days. Let's see if we can open Safari here. Ah, there are days. Familiar with days? To find your favorite data, you go to, I don't know if you're familiar with days, but this is how you can do it. And what was the name again? It was TJ 1132. No? Sorry? Two? No, it's I think it's public, isn't it? Public data? That's not okay. Wasn't it 1132? Ah, there you go. Yeah, it is public. So yeah, let's see the key, file key here. This was the data set we wanted. So this is how you download it, but I've already downloaded it, so we don't need to do it. But what you want to do is that you want, I should show this. You want to download all the data products. You don't need all the data products, but that's the safest thing. I will come back to what files you actually need. If you're downloading from the CHEOPS archive, you don't have this option. It's a little bit different, but you can still access all the necessary or required data files. So let's now go to this data directory here. Okay, maybe I should here. You can see it like this. So the data are organized inside the data directory that is called CHEOPS data into targets. Targets are folders where you save the data. So here is our target. And here is how it comes from days. So I usually just rename it because it's a bit cumbersome, but you don't need it. You can call it whatever you want, but I usually just shorten it to this, a shorthand. And this is all the data that we download from days. Is contained here, including something which is very useful is the data reduction report that you can check out. Here you can see the light curve and all the details about the instrument. I mean, you don't need this, but I find it very useful, especially to check out what the background looks like. Here you can see it's a very strong, very busy background. Yeah. So now let's start this. So what I do is I have, I'm sorry, the font perhaps is too small to see. Centric, Command plus. Okay, thank you. Yeah, it seems to work. So this is what I have defined. I will come back later to what it all means. So let's just start this because it takes like 10 minutes. And so the way I started is just, well, I can first check what kind of scripts are here. Yeah, you just type red and then reduce this. And then we just, okay, it starts. So it starts to extract the data. And here are log files that describes what is currently happening. But let's go back to the presentation now, because now I want to show you what files you actually need. So first of all, these are files that you download from the CHEOPS archive. You can download the flat. So these are the 5 or 6 different kinds of calibration files that are used by pipe. The first one is a gain correction. It just is used to compute the gain. You can also, if you don't have it, you can actually define the gain to something, but why not just download it from the CHEOPS archive? It's available. The second one is provided by me because it's not in the CHEOPS archive. It's a nonlinearity correction. Then we have the flat field, which is the really the biggest one. It's 1 gigabyte in size, and it contains the flat field as it was measured before launch, but that's what we use. And the flat field is dependent on the temperature of the ACD of the star. So it's a big cube, that's why it's 1 gigabyte for the whole sensor. And then we have 3 directories, which contain, first of all, the PSF library. And that's also something you can get from me, or you will get from me. And this needs to be updated for specific changes of the target on the detector. So if you change, like we will do soon, we will change the location of the star on the detector to the center. Then I will need to update this library and provide new PSFs that are part of this library. Then we have bad pixel library and dark frames. Now those are provided by the SOC in the CHEOPS archive. You can download them from there. So you can find, well, pick one that is close to your observation. So they update this every few weeks. There are new maps, and just pick one that is close to your observation to have a current bad pixel map and a dark frame map. So you can just put everything you download into those directories, because pipe will pick the ones that are most appropriate for your observation. And then when it comes to data input files, these are the files that are actually used by pipe. All the rest you get when you download everything is just good to have, but not necessary. So first of all, you have the attitude information that contains pointing, roll angle information, those things. Then you have a file with extended housekeeping parameters that are used. And this is used to compute the gain, is the temperature of the detector, and things like that, or the electronics. Then we have a star catalog. This is used to describe define the background, because pipe actually does produce a model of the background that it subtracts from the data to reduce the effect of background stars. And then you have the actual subarray cube and the imaget cube, if you have imagets. Those are the data that you need for pipe. Well, you don't need imagets data if you don't, I mean, you can do photometry on the subarrays as well. And okay, so this is what we used in the script that I just showed you, slightly different, but first you start by importing pipe param and pipe control classes. And pipe param, it's just a class that collects all the kinds of different parameters that you input into pipe. That describes, I mean, different things like how many principal components you want to use for your extraction and so on. You can probably get by the defaults, but if you want to change anything, it's this, all parameters or the most important parameters are described in the documentation, in the manual, so you can check out what to use. So the way you run this is that you first produce a parameter object called PPS in this case, by giving it two arguments. One is the target name and then the visit name. And these names you can choose yourself, but they need to be in the root directory of the data root directory located there. And then you use this parameter object to put it into a pipe control object, which contains a lot of control procedures. And the one we're using here is process eigen. Eigen, probably not the best name, but what it does is it's just extract photometry using the principal component analysis that I just described. The time depends, of course, on your resources, on the kind of visits and so on. But typically, I would say for a small visit, it's around 10 minutes. If you don't for subarrays, but you can scale it to all kinds of. Let's see. Yeah, let's see how far we are. So what pipe is doing now, we can just go through the log here. It's first of all, these are all the parameters that are. It just dumps them in the log. Here it tries to find suitable point spread functions. So what it does is it checks the parameters that are relevant for this visit. That is the location of the detector. It checks the temperature of the star, which it gets from the star catalog of the target. And then it checks also what the range is for this therm front 2 sensor, because that also affects the shape of the PSF. And then it selects PSFs. In this case, it selected 13 PSFs, and it decomposed those into 10 principal components that are then used. In this case, I define a clip value of 1, which means that it will only use the first principal component. It won't fit the other ones. And this is just to save a little bit of time for this specific presentation and demonstration. Let's see, 31, 38. So that's been 7 minutes. I would expect them to be like 2 or 3 minutes more. You can also see here that I defined the number of threads to be used. Oh, so where is this? Oh, wait, we can check it in the spider here. The number of threads to 8. Okay, so we can check here. So here I did this from pipe import these two things. I defined the target name and the visit name. 8 threads. If you leave this, if you don't define it, it will use as a default, it will use all your CPU's cores, which in this case is 8. So clipping, number of principal components you want to do for the fit. You have to define this yourself. Typically, 1 is good for faint targets. If you have a very bright target, then it becomes more sensitive. The precise PSF shape becomes more sensitive. Then you can afford to use more components to better define the PSF, up to 10, I would say. We are not, in this case, fitting the background stars. Set it to false. The default is that it will fit the background stars as well, the brightest one anyway. But that also takes a lot of time. And since we have an awful lot of background stars in this case, I mean, it would take probably an hour or so. I'm told that we don't have that time. So we're just, so this is just forward modeling where we have the catalog and we just scale the flux with the known magnitudes of the stars. And then we run this. And you might also see here, we have a peculiar line here in the first line. And this is just because multi-threading is a little bit ad hoc in Python. Sometimes it can go wrong if it sort of self-references or something. And this is just a way to avoid that. Yeah, you just put it in and it works. So. Okay, so it's still working. So let's see what the data products are while we're waiting for the actual data product. So what will happen now is that the data products will be put into our visit directory under a subdirectory called output. And then in that subdirectory will be another subdirectory that is the run ID. So it starts just 0 and then it just counts up 1, 2, 3, and so. If you want to do different reductions, you can just run them consecutively with different parameters, say, and you will get different directories, so you don't mess up the. Oh, there's something happening. Okay, so it's now it started to extract it. So this whole time, it was only modeling the background. It wasn't extracting anything. Now it has started to extract, and it's using a first iteration now. The first iteration is used to identify all the bad pixels. So you see, this was pretty quick, the first iteration, because it's only one star it needs to model. Now it's already in the second iteration, and it will soon be finished. It takes only 30 seconds or so. All right, but what you get in this output directory is the target, the light curve. It's a fits table essentially. If you have a subarray, it's called the target name plus underscore SA. If it's imagettes, you get underscore IM. And in this table, you have different columns. You have the time, you have the flux error, you have the background, you have the roll angle, you have the position, the coordinates on the detector of the target, because there's some jitter, so it moves around. You have that. It's good for trending. You also have the various principal components, the coefficients, and these U1, U2, U3, it depends on how many you were using. In this case, we only use one, so we will only have one principal component, but this is helpful for the trending in general. And then you also have a flag, and this flag, let's see, do we have this flag? Okay, this flag decides various quality indicators for the data. Say you have a satellite crossing or a big cosmic ray in the way, or the target suddenly moves out of the field, then this flag flags it. So you don't have to use those specific data frames. It's described in the manual exactly what those flag values are. And then you also have the diagnostic file, the log file, which is essentially what we see here, but in a file. And we will also have something which is very useful, is the residuals. So it produces a model of what it thinks that the data looks like, and then it subtracts that from the actual data. And then you have the residuals. And then you can look at those residuals and see whether or not the model is successful or not. So typically, here you have an example of residuals. To the left, you have something which doesn't fit very well. So the PSF here is not quite good. While in the right one, you see there's mostly white noise. You don't see lots of structure here. So this is, I would say, a successful extraction. So it's quite useful. And then you also have the cubes that define what pixels were masked, the error values used, etc. So you can configure a lot of different outputs. Like here's an example of all the pixels that were masks. And also if you have cosmic rays, those are indicated here. Yeah, so here's the residual. This is what it looks like. So you have the star. To the left, you have the data as it comes, the raw data. You have lots of hot pixels, as you can see. You have the target, and then you have a background star, which is quite bright. To the right, you have the residuals, where we have subtracted the model for the data. So we didn't model the satellite, so it's still there. We modeled the targets, so here's just the residuals from that, and we also have the residual from a background star that was also modeled. And then in addition, you have these telegraphic pixels that can show up as black or white dots. And we have the cosmic rays here. So this is what it looks like. So let's look now at the data that we produced. So it's finished. And this is, as I said, it's just a fits table. You can use your favorite fits table reader or whatever. Let's see, I did my, okay, let's see. I produced one myself. So here's the data. This is what we extracted. So you can see the GJ1132, the one. And I actually downloaded the old graph was for the previous pipeline, the DRP. And here you can see that DRP14 does a better job than the DRP13 did. But you still have this roll modulation. and it's the transit is here is much easier to see in the PSF extracted data. And that was all I planned to present. Yeah, except
thank you very much.
Right. Well, thank you, Alexei. Well, that brings the TS2 section to a close. But I guess we should invite questions for Alexei.
So Monica, and then I propose that we have Olivier finally.
So I have a question. I'm sorry if I missed it, but what paper should people cite when they use pipe?
Oh, yeah, good question. Well, in the past we have used pipe a lot for CHEOPS data, and I would say for now we can cite some of those where we describe. We don't have a full description of the pipeline, but maybe sufficient, like the early papers where we describe it, like Morris.
Because I mean, I'm seeing all the work that you're doing, and I think it would be nice to have a Brandecker et al. To cite, no?
Sure. Yes, it is. Yes, yeah. We have to start work.
A follow-up idea to that. While the paper is in preparation, there's the ASCL, I think, right? The Astronomy Software Code Library, where you can simply add your GitHub link or the pip, and that's also citable, has a DOI as an ADS Harvard.
Oh, yeah,
It might be a nice temporary solution until the paper is out. So you can cite the ASCL and Brandecker et al. In prep.
Yeah, sure. Okay.